Assalamu alaikum. Welcome to the fifth recorded lecture of Digital Logic Design. I am Dr. Khurram Naveed and I am going to be your instructor in this lecture. So, in this lecture, we will cover the topic of a decimal adder design in the first part, and then in the next part, we will design a binary multiplier. So, let's begin with the design of a decimal adder. Suppose we are given these two decimal numbers, and we need to add them. So, in decimal addition, when we perform this decimal addition on paper, we first add the decimal digits in the units location, and as a result of this addition, the we will write 4 here, and because the 7 plus 7 is 14, so we break down this 14 into two parts, where this 4 goes to this location and this 10 goes to the tens place. And since this place digits at this place have the weight 10 times the weight of the digits in this location, this means this 10 will become 1 when it goes to this location. So right, so now we will perform addition of these the digits at the tens place, and here the answer is 9, right? And similarly, next we add the digits at the hundredth place, and here the answer is 3. So this is how we add two decimal numbers on paper. So uh, so we can mimic this whole process um, for decimal addition in computers, um, um, if we can design or devise an adder that adds two decimal digits. Right? So if we can design that, then maybe we can follow the exact process that we followed in the design of 4-bit binary adder, where we first designed the an adder for 1-bit addition, and then we extended it to multi-bit addition. So here, if we could design an adder that could add that could perform one digit decimal addition, then maybe we could extend it to make multi-digit decimal addition, just like following the process that we just discussed, right? So in order to do that, the idea is to use binary codes as a substitute of the decimal digits, and perform addition on the binary codes um, individually, binary codes corresponding to a certain digit and individually, and then move to the next addition, right? So a BCD is a very good option in this regard, because generally BCD contains the binary with some extended bits, right? Binary of the digit with some extended bits, right? So, so if we are adding these two numbers, say, so, so I'm taking a simple example to begin with, and then I will discuss a complex example in the subsequent. part of this lecture for more clarity on this. So let's suppose we are adding these two numbers 1, 4, 6 and 1, 2, 3, right? So in order to add these, um, we simply we add this 6 into 3, we get 9. We add this 4 into 2, we get 6, and we add this 1 into 1, we get 2. This is how we perform decimal addition on paper. So let's mimic this using these codes, right? So if we, instead of 6, we use the BCD of 6. So BCD of 6 is 0, 1, 1, 0. And the BCD, or instead of using 3, we use the BCD of 3, which is 0, 0, 1, 1. So in this case, we get 1 at the answer, and here we get a 0 and a carry here, which results in a 0 here and a 1 here, right? So and if you just look at it, this is the BCD of 9, right? This is so the answer of this 6 plus 3 is 9 here, and here again using this the BCD codes we get the same answer, right? And in this case, when we perform this addition using BCD codes, uh, let's see, 0, 1, 0, 0 and 0, 0, 1, 0, we get 0, 1, 1, 0, and which is 6, which is the BCD of 6. And we also here we get this answer 6, right? So again we get we get the correct answer when we perform this addition using BCD codes. And here again, as you can see, we can perform this addition using BCD codes. So 0, 0, 1 and 0, 0, 1, and when we add these two, we get 0, 0, 1, 0, which is BCD of 2, right? And so this is 2. So this means so the answer using BCD codes is exactly the same, the answer that we got using the um, actual decimal digits, right? Of course, there are going to be some challenges. In fact, the previous example that I used to demonstrate the binary addition actually had that, the decimal addition. The first example that we used that I used discussed to show the process that we follow on the paper to add decimal numbers. So that particular example had that challenge. So that's why I had to change the example to just to give you an idea how decimal addition using BCD actually works. So now in the next we will discuss a bit more complex problem. So now to get a deep insight into the problem, let's take another example. Uh, Suppose we have these two numbers. And we want to add them, right? So um, uh, generally on paper we add each decimal digit individually, like we perform this addition first and we get a 7 in the answer, and then we perform this addition and here we get 9 as an answer, and here we perform and then we perform this addition, and so in this case we have 13, and where we keep 3 here and 1 goes to the next decimal addition, and as a carry, and here we get the answer as the 12, and we keep 2 here and 1 goes to the next place, right? So in order to mimic this process, we thought of using BCD codes for each digit. So let's do that here again. So to have a more deep insight into into this process, and maybe see what kind of problems we may face while doing so, right? So let's let's perform this addition based using the BCD codes first. So BCD of 4 is 0 1 0 0, and BCD of 3 is 0 1 1. So when we add these, we get 1 1 1 0. So this is BCD of 7. Okay, so far so good. And here we have 7, right? And BCD of 7 is 0 1 1, and BCD of 2 is 0 1 0, and when we add them we get 1 0, 1 carry here and a 0 because of that, and here. So this is the resulting answer, and this is basically BCD of 9. And now we move to, so this is also correct, it works. So, and now we move to the next addition, this addition, where we add 6 into 7, and here we get um, so the BCD of 6 is 0 1 1 0, and BCD of 7 is 0 1 1 1, and when we add these we get 1 here, 0 here, and the carry, and then 1 here and 1 here. So we get a 1 1 0 1, and let's see what this is. So if you look at it, this is not a BCD code, right? So in the previous slide, when I wrote down the BCD codes, so the BCD codes went from 0000 to 1001. This corresponded to 0, and this corresponded to 9. But this particular binary number corresponds to a number that is greater than 9, but it can still be represented using 4 bits, right? So this means this is a possible challenge that we face here. So one thing is clear, that this number is greater than 9. We may not be able to interpret it yet, but it is greater than 9. So because in binary it is actually the binary of 13, right? So it means in the next edition, when we perform this next edition, we will have a carry. So um, so the BCD of 5 is 0 1 0 1, and BCD of 6 is again 0 1 1 0, and when we add these, and there is a carry because this is greater than 9, and it means we will have a carry. So we do not know what this stands for in BCD. We have yet to figure it out, but right. But one thing is clear, that we will have a carry to the next edition, and in this case, since the carry is always going to be 1, if there is a carry, it will be either 0 or 1. So in previous editions, the carry was 0 0 0. So the 0, and the BCD of 0 is 0 0 0. So I mean, it is like we completely ignored it for that reason. But here we have carry 1, and in this case we will have this BCD 0001. So now when we add these, we get 0, and then we get a carry. So now we are adding 3 binary numbers, and 0 and 1 and 1. Okay, so this is the binary of 12, but still it is um, it is not a BCD, right? So, so here we have a few bumps on the road. We need to figure out a way to interpret uh, uh, 4-bit binary numbers which are greater than 9 and find a way to convert them into BCD. So in order to do that, let's see how and how the numbers greater than 9 are coded using BCD and binary. So in binary, 10 has um, a code as 1010, while in BCD 10 is written using two BCD codes because it has two digits. So first we will write the BCD of 1 and then we will write the BCD of 0, and similarly 11 has binary of, so in BCD we write the BCD of individual digits. This is decimal, right? And 12, so BCD of 12 involves BCD of 1 first and then a BCD of 2. And similarly in 13, in case of 14, we have 1 1 1 0 and 0 0 0 1 and uh, okay. So by looking at this sort of a truth table, we can maybe figure out how we can convert between these um, these binary numbers to these BCD codes, right? So just as you can see, we in all these numbers we have these three zeros. So if we just ignore them because these are zeros, and um, having zeros before any binary numbers is inconsequential. So if we just concentrate on uh, these five inputs, so and then we see this is the binary of 16, right? So and this is the binary of 17, and this is the binary of 18, uh, 19, 20, 21, right? Um, and so by just if you look at it, by just adding 6, we can go from each of these binary codes to BCD codes, right? So if we add 6 in 1010, we will move to, we will have this binary number which is 1 and then 4 zeros, and again when we add 6 here we will go and to 1 and then 3 zeros and then 1. So if we want to convert from this non BCD code to a BCD one, then we need to add 6. This is the possible solution. So let's see whether it works here or not. So if we add a 0 1 1 0, and here we get a 1 and a 1, and 1 plus 1, 1 is 0, and so this is the carry, and again 0, and this is 1, right? So we have uh, a BCD code of 3 and a 1. So let's just put 3 zeros in front of it, and so and this is our carry, and this will go here, right? So now if using using this example, we have realized that by just adding 6 in the BCD of numbers of binary sums which are greater than 9, um, we can easily go from from a non-BCD code to a BCD code. And similarly, we can do the same thing here. We can add a 6 here, and here we will see will 0 1 0 and a 0 and a 1. So this one is the carry, and it goes to the next addition, and since there is no next addition, so here this is the binary of 2, sorry, BCD of 2. So the answer is now 1 2 3 9 and 7, right? It is exactly the same answer that we obtained here. So although in some BCD additions we had to perform some extra manipulations um, given here, but we found out a way to fix this problem, right? So now since we already have a 4-bit binary adder, we have already designed a hardware for it. Uh, so so this means we can use this 4-bit binary adder to perform um, a decimal addition of two BCD codes, because BCD codes are already, we know that are in 4 bits, and this is a 4-bit uh, adder. So we have a piece of hardware that is ready for us to use, and we have now figured out a way that how we can use it, right? So now it is important to find out the conditions as to when we need to add this 6, because it is not always necessary. Here we do not need, we did not need to use this um, to add this 6, but in next editions when the resulting answer was not in the BCD, and at that location situation, in that situation we needed to do that, right? So this is how we can make 4-bit binary, so 4-bit BCD adder um, using uh, two 4-bit binary adders um, to add two decimal digits, where this may be the BCD of uh, first decimal digit, and this may be the BCD of second decimal, right? So, and in case where this binary sum is greater than 9, we need to add 6 here. So this is 0 0 0 1 1 0, which is 6. So this binary adder is here to add 6 to the binary sum. Rather, I need to write it to the binary sum um, when this sum is greater than 9. But so now the tricky part is to um, detect whether the sum is greater than 9 or not. So if the sum is greater than 9, then the next adder should add 6, and if sum is not greater than 9, in that case we do not need to add anything, right? So in order to design a circuit to detect whether the sum is greater than 9 or not, look at this truth table. that on this side plots lists the possibility of binary sum in 4 bits, where this k is the carry of this adder. So and this is the corresponding BCD sum, right? So for the first part of this table, so for the first part of the upper part of this table, the BCD and the binary look the same. So it means here we do not need to change anything. But for this particular part of the table, we need to be able to detect these numbers to add 6 in these numbers and get the corresponding BCD sum, right? And which for that reason we have attached this 4-bit binary adder to add this 6, right? Uh, okay. So in order to detect these numbers where we have gone from 10 to 19, because maximum sum of two BCD numbers is it can be 19, right? So if say one BCD digit is 9 and the other is also 9, which is the maximum value of a digit, and we also have a carry, an input carry from the previous BCD addition, and in that case the sum becomes 19. It means the sum of two BCD digits will be either greater than, sorry, either less than or equal to 19. So this is why this whole we have listed here, we have listed the possibilities of first 9 digits, 19 um, uh, possibility of 19 sums, right? Okay. So um, so in order to detect uh, these numbers where we need to add 6, um, let's just compare this part of the table, this part, so this part of the table with this part, and let's see whether we can find some differentiable properties to differentiate between the first 9 digits and the subsequent ones. So if you look at it, let me erase all the extra stuff. So right, so just observe from here that for this, if k is 1, we can so k is also 1 for sorry, k is only 1 for 16, or for a number either 16 or a number greater than 16, right? So this means if this carry k is 1, it means we have the sum, this sum is either 16 or 17 or 18 or 19, which means we need to add 6 in that, right? So this particular output can be a possible condition to detect uh, uh, these numbers, right? And in case of these first two digits, 10 and 11, if you look at it, let me change the color. These two bits are on simultaneously, but these two bits are not on in any of the previous situations. Here, as you can see, these two bits are on, but these two bits are not on. And here, these two bits are on, but these two bits are not on. And similarly, although here these two bits are on, but here these two bits are not on. So this is the only instance where these two bits are on, which means we can detect 10 and 11 by just taking the AND of Z8 and Z2. In case where the AND of Z8 and Z2 is 1, it means the sum here is either 10 or 11, right? So now we have devised conditions for or found out conditions for at 6 digits, that is 10, 11, and 16, 17, 18, and 19, right? So now just if we just look at these four, or rather need to just look at this. So here, for 12, 13, 14, and 15, these two bits are on, and this condition never arises in any other situation, right? So here, although we have four, Z4 is 1 for 4, 5, 6, and 7, but Z8 is absent, right? So this means this condition is only present here. So it can help us detect 12 numbers from 12 to 15 when they are in the sum, right? So this means this AND gate between Z8 and Z4 uh, may be a possible circuit to detect these four numbers, and whenever this AND gate outputs 1, it means we have detected either 12 or 13 or 14 or 15. So now let's make this circuit, right? So um, move the unnecessary stuff, right? So let's make this circuit. We have this input as a possible condition, an AND gate between Z8 and Z4, and an AND gate between Z8 and Z2. So whenever any of these outputs are 1, it means we have detected a number, sorry, the sum is a number that is greater than 9, right? And in that case, we need to add 6. So so whenever this output is 1, let's just connect it directly to these two inputs. So whenever this output is 1, we get a 1 here and a 1 here, and we already have given 0 here. So this means this will be 0, 1, 1, 0, and it will add 6 to the sum to convert it from a non-BCD digit to a BCD1, right? Or rather non-BCD code to a BCD1. So now after these modifications, we have now successfully developed um, um, uh, a BCD adder, or a decimal adder, that adds two decimal digits. In a drawing of a decimal digit is given here, that is taken from your book. So this is the end of the first part of this lecture. In the next part, we will design circuitry for logical circuitry for uh, uh, binary multiplication.